You all, and thank you for taking the time to join us today. I will first address some logistical issues for the session and then introduce our speaker, Forrest Breyfogle. A lot of material is planned for this 1-hour webinar, so the audio will be muted for the remainder of the presentation. We will not be able to hear you, but you will be able to hear Forrest. Do not let this stop you from sending us text questions through our system during the presentation. If Forrest cannot answer your question either during or at the end of the webinar, we will either email you or call you with a response. There will also be a recording of the webinar available on our website within 48 hours. You will receive an email with a link to the recording. I will now introduce our presenter, Forrest Breyfogle. Forrest is a professional engineer and ASQ fellow. He has authored or co-authored 13 books and published over 150 technical articles. He recently completed a 5-book set, Integrated Enterprise Excellence, which provides radical management advancements in the utilization and integration of scorecards, strategic planning, and process improvement. Forrest was named the Quality Professional of the Year for 2011 by Quality Magazine. He also received the prestigious Crosby Medal from the American Society for Quality in 2004 for an earlier book, Implementing Six Sigma 2nd edition. Forrest is currently located in Austin, Texas, where he founded Smarter Solutions in 1992. Again, thank you very much for joining us today. At this time, I will turn the presentation over to Forrest.
Okay. Well, it's good to be here. I'm glad that we've got quite a few people tuning into this webinar. What I'm going to be talking about today is some issues with XBAR and R control charting and also process capability that's related to this. Now, in reality, there's issues with P charts, U charts, and C charts for some of the similar reasons, but I'm not going to be touching on that today. I'll then be describing what I call 30,000-foot level means of actually reporting and being a better alternative, in my mind, to the traditional approaches on how we look at data, in particular for the XBAR and R chart. So the content of this webinar is going to be taken from various sections from the 3 books that you see in front of you there. Well, if we examine a control chart, in all cases, what you'll have is a couple red lines there that are shown as upper and lower control limits. So the variability of the data creates those control limits. So if you've got a large amount of data, you're going to have wider control limits than if you've got a less amount of data or less amount of variability. So if we have data that's within those control limits, then what we do say is our process is stable. Now, if we have a situation where one is outside the particular control limits, then we can say that's special cause, and we can take action to try to resolve that particular issue. Now, given for a certain set of data, we can have different means of actually creating a control chart. So, for example, if you see on the right-hand side, it comes down from continuous or attribute decision point to the defectives or defects. Defects or defectives. And that basically leads down to P charts, NP charts, C charts, or U charts. I'm not going to be talking about those today, but that's part of the decision-making process relative to creating traditional control charts. If you go on the left-hand side, you'll see continuous data. If you've got a subgroup size of n equals 1, that leads over to an XMR chart or an individuals chart. But if you've got a larger subgroup size than 1, then you can lead to an XBAR and R chart or an XBAR and S chart if you've got more data within each subgroup. So this is a traditional decision tree, basically, for deciding which particular control chart you would create using traditional methodologies. So let's consider that we got this data where we've got 10 subgroups So we've collected data over 10 periods of time, and each of those subgroups has 5 samples. So the question would be, which particular chart would we use? Well, if we go back to our decision tree, we come down, we've got continuous data, so we come to the left. We've got n is greater than 1, so we come to that decision point. And we, since it's less than 10, then we're going to do an X bar and R chart. So let's go in and create an X bar and R chart. If we do that, this is what it would look like. Since the red lines are much closer than the other points, we notice that we have many out of control signals in the X bar portion of this particular chart. The range chart doesn't have any out of control signals, but the average value does. Now in reality, we would go in and try to address what's happening for all these special cause conditions. We would say our process is out of control, and we cannot technically describe how we're doing relative to any specifications that we might have. But in this particular section, I'm going to go in and still look into examining the process capability, so to speak, even though this process, using this current level of reporting, states that we're out of control. And I'll be getting back to the particular chart a little bit later. So let's talk about process capability and performance for now. So the idea behind this, we go in and track something over time, and if we've got a stable process, then what we can do is build a distribution, as it's shown on the left-hand side. We can turn that distribution on its side, and then we can, as shown on the far right-hand side, create upper and lower specification limits and put those on the particular graph. And we can decide how we are performing, how the process is performing relative to the specification limits. Got a polling question here. We're going to be leading to what we call CP and CPK and PP and PPK. Those are process capability indices reporting. The question I'm asking here is, does your organization use this form of reporting or not? If you're not sure, or you're not even sure what the concepts mean, just click the box unsure, because we will be talking about those in a minute. Okay, we'll just give it a couple more seconds here. Okay, let's close the poll. Okay, so it looks like we've got 48% yes, 38% no, and 14% unsure. Okay, well, I appreciate that. That gives me a little bit of an idea where we're at relative to the audience that's out there. Process capability performance studies assess how our process is performing relative to the criteria. Statisticians over time have challenged how well this is actually accomplished using these indices. However, customers often request these indices when communicating with their suppliers. Customers may be actually setting up certain values that a particular supplier is to be achieving relative to meeting targets for these particular values. So let's talk about what's actually happening relative to process capability indices. Well, one measure is the CP value. The equation for actually calculating the particular value is quite simple. We just take the upper spec limits minus the lower spec limits divided by 6 times the standard deviation, as shown on the right. Now, graphically, what that alludes to is that if we've got a CP equals 1, we notice how our distribution is pretty much filling up the distance between the upper and lower specification limits. If CP gets equal to 2, we can see that the width of our variability of our process is about half of the overall width between the upper and lower specification limit. So what's the implication if we had a CP is equal to 2? That's basically saying the width between the spec limits is about 12 standard deviations of our process. Now with these calculations, there's some underlying assumptions. First off, we have to have an upper and lower specification. And for us to really use these manual equations, we need to have a normal distribution. Let's next talk about CPK. CPK addresses how our process is relative to being centered within the upper and lower specification limit. So mathematically, we'll have the relationship that's shown on the right-hand side. What's the assumptions relative to this? What's the value of CP of 1.0 really mean? Well, it means that the process average is 3 standard deviations from the closest specification limit. The next thing we have relative to process capability indices is PP and PPK. Now this form of metric reporting is different than CP and CPK. PP and PPK uses all the data, where CP and CPK is looking at and eliminates between subgroup variability. So that can be a really big deal. So we're going to be really elaborating on the implication of this. Because a lot of times people asking for CP and CPK, and they think they might be getting PP and PPK as a customer. But that can be a really big disappointment. It can cause a lot of confusion. Process capability equations are really quite simple, but they're very sensitive to the standard deviation input. There's really a lot of difference of opinions and confusion around the standard deviation calculation. Equations are for normal distributed data. Now programs can actually address it if it's not normally distributed. However, we need to check for normality before using these equations. The other thing that's very important that people often ignore or not consider religiously as I think they should be, these calculations are only valid for a stable process. But then the question is, does everybody determine process capability stability relative to, is it always going to be the same thing or not? Is there confusion relative to that too? I'm suggesting there is. Let's look at the means of calculating standard deviation. So I'm showing 6 different approaches for standard deviation calculation shown here. Now, if you've got data from the X bar and R chart like we just did, you would calculate standard deviation using method 2. The average range value divided by D2, just a constant dependent upon how large your subgroup size is. If you have an individuals chart, then you would be using method 5. Well, now you're looking at the variability between the subgroups. Quite a bit different there. It could be. Well, what about PP and PPK? Well, that's using long-term variability. That's more aligned with method 1. Now, if you're using a computer program, all these calculations are behind the scenes, and you don't really know how it's actually calculating it. because it's just giving you a value. But it's really important to understand how these particular values are actually calculated and the implication behind that. So process capability has numerous issues. Often we need to have, we report CPK, but we really need to have CP and CPK to convert to parts per million, or defective rates.
Hey, Forrest, I have a question for you.
Okay.
How do you know which method to use?
Well, what I'm going to be suggesting here is that you go in and look at them completely different. Right now, what I'm focusing on is what's wrong with CP and CPK. And PP and PPK for that matter. What I'm going to be leading to is that you shouldn't do any of them, and that there's a better way of actually reporting, and I'll be getting to that in a few minutes. Because if you start thinking about how confusing this is to you, and we're probably practitioners here, what do you think about when we report it to a CEO or a high-level manager or even an operator? Just think about all the confusion that can happen there. And we're going to be addressing that before we get done. Now, if I didn't do a good enough job or there's still confusion, please ask me at the end.
And another question is, what is the standard for CPK?
What is the standard for it? Well, not sure exactly what you mean. You might mean what is an acceptable value for CPK. You know, Six Sigma suggests that it should be 1.5 or greater, and if you've got other people before Six Sigma, they talk about 1.33 are better. But that's what you mean. But what I'm suggesting, those numbers can be rather confusing, and also we don't really understand a lot of times the confidence interval that we can have relative to actually calculating those values. So to me, it's just a bag of worms, and that there's a better way of actually presenting how our process is performing relative to what we need, and I'll be getting upon that just in a few minutes. And again, if I didn't answer that adequately, please ping me at the end of the session here. Process capability also has issues like we just talked about, how standard deviation is calculated. And that depends upon how the data is collected. Again, it's commonly requested, but in my mind is poorly understood. So let's get back to that data that I showed you previously. So I can still, even though I shouldn't really do it, I can go in and create a process capability indices chart. Now if we examine this chart, we notice that we've got two different distributions. The red one is within, and the black one is overall. So the within one represents what we can expect from CP and CPK. The black one is what we expect from PP and PPK. Now if you look on the right-hand side of this particular graph, you'll notice that the CPK value, for example, is 1.44. But if you look at the PPK value, it's 0.3. That is a huge difference. Now, if we go to the bottom of the chart, we'll see that we've got within performance to be PPM total of 8.19. Well, that's pretty good. But if you look at the overall performance, it's 268,525. That is not good. That's saying you've got about 26% non-conformance rate. So which one is right? Well, I'm suggesting the long term is really what is more interesting to the customer, because where the other one is just dealing with short-term variability. But there's more to the story. What happens if we only examine one sample per subgroup? So I'm just taking now the first value in that subgroup. If I did that and I create an IMR chart, notice now I'm saying our process is stable. It's in control. That is very different than what we had previously. If we then go in and do a process capability statement or graph on this particular set of data, notice how the red line and black line are really close to each other. And also notice how the PPK and the CPK value are very close to each other on the right-hand side of the graph, and they're similar to the previous PPK on the X-bar and R chart. If we look at the within performance at the bottom of the graph, we notice that we got 260,739 versus ppm total of 274,322. So this is more in line with the PPK value that we had previously, or the overall. So why is that? It's a very different way of doing it. Now notice, both of these are a legitimate way of looking at the same process, and you get a dramatically different answer for how you're reporting performance. Now, there's another way of actually presenting the data of how we're doing relative performance. Now, a lot of times if you've taken Six Sigma training, we'll talk about a probability plot. And more often than not, people plot the data to see if it's normally distributed. And if it's not, guess what? They go into cold sweats. Shouldn't go into cold sweat. We may be able to do some transformations and deal with it. But what I'm using it here for is a probability plot to describe how the process is performing relative to what is needed. So in this case, we got spec limits of 95 and 105. So for the x-axis, that's where we put the values. And then we notice on the y-axis, it's got percent less than. So we're basically looking at the area under the curve to the left if we go up 95 and say that value is about 7.8%. We take the 105 value and go up, we get about 80% to the left of that, or about 20% to the right. So now we really want to look at the area, or the percentage that's beyond 105 and 95. So if we go through that, we get 26.4%. Now if we compare that value to the capability of one sample, notice how we get the same number. Just express it a little different. We say 27.4% versus 274,632 parts per million, which is basically the same number. But what I'm suggesting, a better way of reporting it is using a probability plot. And also, if the data are not normally distributed, like a log normal, I can still do the same sort of thing and make it a transformation and present it in non-transformed data, in non-transformed units. Now let's compare these two control charting approaches. Look at the very different responses that I get if I did 1 versus 5. The actions that someone would take on the left-hand side would be very different than one on the right-hand side. Now the question is, which one's correct? Okay? Well, what we really have the difference between the two charting is that the X-bar and R chart has the variability within subgroup. That's how they calculate it, where now the variability between subgroup is what is done on the individuals chart. So that's what the real difference is. So the variability between subgroups has absolutely nothing to do with the control limits if you're plotting an X-bar and R chart. Now the question is, which one's correct? If we go in and look what Demings has said, makes a statement about the fault and how we get into a lot of firefighting and blame people about things, and we think it is a special event. We look at speak of faults of the system as common cause of trouble, and faults of fleeting events as special causes. And he suggests that there's a lot of confusion between common and special causes. And he also talks about more often than not, we have common cause issues relative to special cause. Now, the question I ask is, from the previous chart, should we go in and look at the X bar and R chart or the individuals chart relative to Deming's point of view for common cause variability? So to illustrate this point, I do this on a lot of my presentations. I'll build a situation. I'll talk about a manufacturing situation, but the same applies to transactional situations as well. So let's consider we have a manufacturing process where we get a new batch of raw material every day of the week. And it truly affects the response of our process. So that's going to impact the quality, perhaps, or a dimension or some other aspect of our process. But we don't know that. Now, I said that it affects it, but I didn't say it affected enough to make it a bad part. Now, the question I ask is, should the ups and downs that we have from the day-to-day variability of the raw material lot, should that be a source of common cause variability or special cause? Now, when I present this to classes, invariably they'll say it's common cause variability. So what's the implication of that? That's saying the variability between subgroups should be impacting our control limit because we believe that affects our view of how a process is performing relative to stability. So that's suggesting that X bar and R charts should not be used for what I call 30,000-foot level reporting because the variability in an X bar and R chart is not impacted, or between subgroup variability does not impact the control limits on an X bar and R chart, as in 0. So if we've got variability between subgroups and we have an X bar and R chart, we can have false signals relative to our belief system. To me, this is a very big deal. Now, there are situations that an X bar and R chart could be applicable. If you've got a manufacturing process and you want to go in and make sure I don't have any variability between subgroups, and I know I'm going to adjust my process when I do have that, then you could use an X bar and R chart. But for a majority of charts that I've seen, that we are not actually trying to accomplish that. We're just looking at subgrouping. And if there's variability between subgroups, and where we should consider common cause, then we can have false signals. Now the question often gets asked, well, what's the implication on this in transactional processes? So let's say, for example, we're looking at the hold time in the call center. The implication of this is what is the frequency we are using to determine our subgrouping. So let's say, for example, in the call center we get more hold time on Monday, perhaps because people are not getting a chance to call in for Saturday and Sunday. So let's say Monday has got a longer hold time. So if we went in and actually plotted every day of the week, then we would have a blip every Monday. So that, to me, that Monday variability is a source of common cause variability. So we'd subgroup it by week. So as you can see, we're not at this 30,000-foot level reporting point of view. We're not really trying to take timely intervention to manage the process. We're providing a high-level view of how the process is performing. So what I've got here, and it's perhaps a little hard to see here in great detail, but this is the decision chart that I use for creating these 30,000-foot level control charts. Now notice also at the top I'm pointing to several of the control charts where it may be appropriate to do a transformation. And this is especially important when you've got a measurement that's perhaps bounded by 0 in the case of time. How long does it take to do something? You can't have negative time. So that's going to be bounded by 0. So then you would want to go in and maybe consider a transformation of that. Because the control chart is only to address stability. The probability plot in the case of continuous data is to address how the process is performing relative to specification. And I'll blow this one up a little bit further since this is a particular situation we're talking about. We got continuous data in step 3.2.2. All transactions available are, we've got sampling in this, so samples from our subgroups, so that would be there. And then we determine infrequent subgrouping and sampling, just like I talked to you about as a day or a week. And then we're going to do an individual's control chart of the mean and standard deviation of subgroups. And you might want to take a transformation on standard deviation because it can't get below 0. So let's do that for our particular set of data because I don't like to throw away information. I showed you how we had a different chart for taking the first data point, but I want to look at all the data within my subgroups. So now what I'm doing is an individual's chart of the mean value that I'm having over those 10 different observation periods. And I'm also looking at the standard deviation or the log of the standard deviation of each of the values within the subgroup. So as we see right now, we've got stability using this particular reporting methodology versus using a traditional X bar and R chart. And to reiterate, the difference is because the X bar and R chart doesn't consider the variability between the subgroups, where the individual's chart on the right-hand side does. Now, the next question is how is our process performing? And I like to include this within the 30,000-foot level chart. So right now, the two top charts show that the process is stable. They're showing no shifts or no individual points that's beyond the control limit. Then what you do is you go back to the raw data. So in this particular case, we had 5 samples per subgroups times 10 subgroups, so we have 50 points. We plot that on a probability plot, and we notice now, it's not a really great straight line, okay? And that's kind of understandable, and that's what you'd like to see. But it's pretty close, especially consider we've got basically 2 different distributions. We've got between subgroup variability and within subgroup variability. So to my mind, it's doing pretty darn good. Notice now when we start creating this analysis, we get 27%, which is just about the value that we had when we do an individual's value for each of the particular subgroups. But now we have more confidence in our answer since we've got a greater sample size. Okay, and the next question is, how do we put this together relative to the big picture? What I'm suggesting is that we use this form of reporting for not only looking at widgets in the manufacturing line or maybe even the whole time in the call center, but we actually use this as an alternative to other more common red, yellow, green scorecards, table and numbers, stack bar charts, pie charts, and so on. But I want to align those to what we do and how we measure what we do. So this is called the value chain, and it's an integrated enterprise excellence value chain, where the rectangle boxes describe what you do, and you can drill down those. And we would like to have it all clickable. So anybody has wants to understand procedures for certain things, they can click and find those. Then each of those metrics, or each of the functions, would have metrics relative to quality, cost, and time for the particular function. So for produce and deliver products, we could have lead time, defective rates, WIP, on-time delivery, and period constraint throughputs of financial metrics. So what I like to do is use this form of reporting not only for people in manufacturing, but throughout the organization. So the idea is you click on the oblong icon there, then you would get a chart that would look something like this. So everybody understands how the process is performing. Notice what I've just done is I've eliminated CP and CPK and TP and PPK, which are very difficult to understand, and you often have to have two values to actually describe how it's performing relative to nonconformance. And more often than not, we're just really interested in the nonconformance rate. So in this case, we got 27% nonconformance. So that's common cause variability, and in other words, about 3 out of 10 is going to be nonconforming. The other interesting point about this form of presentation is if you got a recent region stability, we can even say our process is predictable. So I can say this is the magnitude of nonconformance I can expect in the future unless we were going to do something different. So if this is not about a good enough number, then we need to undertake a process improvement effort so that it actually improves the performance, and now we transition to a new level of performance, an enhanced level of performance that's demonstrated by the control chart shift, being that we change, and then the new probability plot describes the new level of performance. So what's next? I kind of got ahead of myself here. Assume that you've done a great set of metrics. What are you going to do? You look at scorecards, lead the right behavior. Is that enough? More action could be needed. And what I'm just suggesting that we want to then analyze all our metrics to determine where we should actually be improving, because some of the metrics maybe have some nonconformance, but we ought to be focusing on another area of the business, or an area of the business that has the most leverage to helping our customers and the financials themselves. So that leads to my 9-step IEEE business system. So if you're interested in that, just send me an email, and then I'll forward you some links to that. Okay, so we covered a lot of ground here. Issues with the traditional use of X-bar and R charts, process capability reporting. We talked about an alternative of 30,000-foot level predictive methodology that addresses these issues. I'd like to, a little bit of marketing here, or at least inquiry, I guess. I'd like to know how you heard about this webinar. We did some things in LinkedIn, and we also send out some email to our database and at Smarter Solutions. We did some Facebooks, and maybe a friend or co-worker told you about this webinar. Maybe I didn't hit it on any of them above. So please let me know what, how you found about it here. Okay. You're closing a couple seconds here. Okay, let's close it and see what we came up with here. Okay, so it looks like a lot of emails from Smarter Solutions, and then it looks like maybe some of those email got sent over to somebody else, or even from LinkedIn. So we did have a few people that came in from LinkedIn. So I appreciate that feedback. So that gives us some ideas what seems to be working and what's not seeming to be working for us, trying to get the word out there and what we think is something that can be beneficial to you. So one of the things I'd like to also, I mentioned my books here, and so it's got a lot of content. Like Volume 3 is like 1,100 pages. It's a whole black belt and master black belt course in itself. And then we've got also Volume 2 is the business system and so on. And then the Lean Six Sigma Project Execution Guide is kind of a memory jogger for Volume 3, 8.5 by 11, so it doesn't exactly fit in your pocket, but it gets into some of those charts that I just described. So those are, if you get on a website and then just do FB for Forrest Breyfogle in the year 2013, then that represents a coupon code for purchasing in that. So what I'd like to now is to have some questions, see what people come up with. Do we have some questions there, Ann?
We've got a few questions. How do you handle data that doesn't fit any transformation, even after removing high or low values? Okay. Well, one of the challenges that you can have, you might have more than one distribution. Okay, and the other thing that can happen is, first off, before you even start looking at the transformation, I'm suggesting that you might need to go in and track it over time without transforming the data. And if 0 is within your control limits
and also it makes physical sense, then you might need to transform your data. But see, what can happen often if you just jump into transformation, if your process changed, then you're trying to basically look at two different distributions in one transformation, which is not the right thing to do. You need to first off look at the stability. The other thing is, whenever you do transformation, as I mentioned earlier, it needs to make physical sense. A lot of times people will use the box-Cox transformation, and you get these bizarre lambda values that I don't know what they mean. But so I'm a big fan of like a lambda of 0, which is for the log normal, or square root. That has applicability, especially for attribute data. And so, and I talk about a little bit of that in the book too, but it needs to make physical sense. But what I'd suggest also is you might have a situation where you got more than one distribution. For example, if you, and if it's a little bit, it's not going to matter, but if you did a 30,000-foot level and you had a chart where one machine was doing a lot better than the other 4, well then, and you tried to put it all together, then you're going to get maybe a knee in the curve, and you've got more than one distribution. So then you might need to look at 4 machines together than one by itself because it's so much different. Understanding that you might be able to learn what's different about that one machine and bring the other ones up to speed with it too. So anyway, that's a couple clues, and if you got something particular, you might touch base with me offline. Okay, got any other ones?
Yeah, we've got several. If we don't get to all of your questions, we will respond to you after the webinar. This question is back to your call center example, and he wants to know which chart you would use to monitor supplier performance.
Okay, this would be for supplier performance. Well, let's go in and, well, I guess it kind of depends. You know, right now, let's say that they're giving you information in batches. Okay, so every day that they give you a new batch. Okay, and we're going to be looking at, for now, just one particular part that they do. Okay, now so then if we could go in and our subgrouping could be by batch. So we might, between batches, actually have 3 days differences or a week differences. So I would think if, for that situation, you subgroup by batch. You could go in and then take 5 parts from that. If we got a continuous response from that, then we could take those 5 samples from each one, and then we go in and do basically the same thing that I did for this particular set of data, where we're doing an individuals chart of the average and the log of the standard deviation, and then we would do a probability plot of raw data. Now, if you have an attribute situation that's purely pass-fail and you can't do it continuous, then I suggest, and it talks about in the books, about doing an individuals chart of that as opposed to a P-chart. Because P-chart has some of the similar issues that you have with the Explore and R chart. So I don't know if that helps give you some little bit of thought on what you might do, and I could touch base with you on other situations that you might encounter.
Okay. I've got another question. How do you determine whether data is normally distributed?
Okay. Well, first off, I'm looking here is we're assuming that it's from a process, and we want to track it over time to see if it's stable or not, and without any transformations on it. And if the value is like 0 value, or say a limit is with that a natural boundary is within that, that's an indicator that you probably need to take a transformation. But I still like to look at that particular chart, because if it's shifted, even untransformed, then the thing is I will stage it, you know. And then if you stage it, then you can look at the data from the recent region of stability. So now we've established that we think our chart is stable. And then what you could do is do a normal probability plot on it to see what it's actually performing. And there's just several of them I like to do. I like to do the square root of the data, you know, and all these would involve lambda values. and then also the zero value here. Now, let's say, for example, it's log normally distributed. If you do that on a normal paper, then it's going to tend to be a concave surface to that. And then you would go in and do a log normal plot on it, and then see if that does it a straight line. And if it does, then I would kind of go with that. But I just want to underscore to me that they should make physical sense and not just be some arbitrary transformation. Okay, got another one?
Yeah. Yes, this person wanted to know your view on leading KPIs and how IEE can help.
Yeah, the KPIs are, people sometimes align those to strategies or key process indicators, and other times they don't. I don't like to line metrics up to strategies. I like to go in and align them up to the value chain that I showed previously, and I actually like to choose my metrics from the value chain. Often what will happen will people or organizations say, hey, these are the 5 KPIs I'm going to do. But to me, you need to really start looking at the overall value chains on your selection of those. And you would like to have it so it's automatically reported. So you pull from your ERP system, and we got software that does that, but it puts it in this particular applicable format that I was kind of describing earlier. And that's where I like to select the KPIs. And I also like to go in and track them using the methodology I just described.
Thank you, Forrest. Can you tell us the minimum number of data points needed before you start control charting?
Okay. The traditional control charts is to identify when we got special causes and stop the presses to fix it. So if you're operating under that mode, you would need to have, 30 typically is what's suggested. However, what I'm suggesting is different. This is at a 30,000-foot level view. So especially if you went in and had a transition to process and you're looking at things that are reported only monthly, like the financials, you may have only 3 data points. So I'm suggesting you plot 3 data points on the probability plot. I understand that the confidence interval around that is not what you'd like to see, but the thing is, if you just got data from 3 points, you got data from 3 points. And you could still provide a best estimate of how it's performing. Now, it's true that you could have a situation where one of those are special causes, but if and you react to it as though it's common cause. But I'd rather do that than the other approach, where I'm having common cause variabilities treated as those special cause. Because if the response is not satisfactory, then I'm going to be actually working on what to improve the process. Because we have to understand, if we've got a special cause condition, we're looking at that particular point, try to figure out what happened there. Whereas if we have a process capability statement that's undesirable, then we're working on process improvement. And if there's a little special cause in there that we've kind of missed, it's not the end of the world, because we're still working on process improvement.
Can you tell us how using an XMR chart, could using an XMR chart hide a potential source of quality improvement?
So first off, he talked about XMR, which would be in individuals with a moving range. Okay, I just showed you how to do an individuals chart and not the moving range. So the individuals chart can also have accompanying moving range chart. The charts are somewhat redundant. The only thing the moving range chart does for you, it tests the big swings between the values for the individuals chart. And to me, I think it causes more confusion than it's really worth. If somebody wanted to do it behind the scenes, that's fine. But as far as the overall reporting, I don't include the moving range part of it. But the thing is, with my reporting point here, is the individuals chart as opposed to the X-bar and R chart. It keeps you from going in and treating the variability between the subgroups as special cause issues, like X-bar and R chart does. Individuals charts don't do that. So to me, and I believe probably most of you agree with me that raw material day-to-day variability is considered a source of common cause. If that's what our true belief system is, we've got to go in and have a control charting methodology that's consistent. and that leads to moving range chart. So moving range charts don't hide anything. Okay, it's all there. Okay, but in addition, at the 30,000-foot level reporting, I am describing the capability of the overall process, which charts, X-bar charts don't do. So I'm looking at that at the same time. And then if you've got a quality issue, the quality issue more often than not, like Deming's statement, 94% of a common cause. So the odds are with us that would go in and report the quality issue that we'd be having. And then what we'd be doing is not addressing an individual point, but we'd be trying to figure out what we could do to the process to actually make it better. And then the proof of the pudding that we actually made a difference is the 30,000-foot level chart, the control chart piece of it, actually shifted to a new enhanced level of performance. And when it did that, then we can make a statement of how we're actually improving the quality by looking at that new probability plot.
Thank you, Forrest. Can you tell us how you calculate the nonconformance percentage from the probability plot?
Okay, I'll show you. Okay, so like in this one here, we had the average mean and the log of the standard deviation. So it's showing that it's a stable process. Notice I am not looking at any of the axes on the standard deviation and the mean values. I'm not. I'm going in and taking the raw data and doing as a probability plot. So the probability plot, you notice that we have on the x-axis, it's the same as the y values on the vertical axis on the mean chart. Okay? And notice now we got percent less than. So this is a normal probability plot. So you can see how it's got normal at the top of the graph on the probability plot. And so now the blue line kind of represents a straight line. So if it's a straight line relative to the data, then we believe that distribution is included or is a good representation or a fair representation of our data. So then in this case we had specifications of 95 and 105. So we come up vertically, so we intersect that line, and we notice we have on the right-hand side 8.452. So that represents as we think is about 8.5% to be less than our lower spec limits. If we do the same sort of thing on 105, we come up and we notice we got 81% or so. That's below that limit. So if you look at the two tails that we have on the outside, so we got like 19% on the above side, and we got about 8% on the other side, so we got like 27%. So that's how we're reporting out that 27% non-conformance rate. So hopefully that helped a little bit to answer that question.
Okay, we have time for a few more. In your experience, how many organizations have used control charting for financial business results?
Well, we're getting more and more now because people are getting into our software and how they're looking at the data. So I go into companies and actually doing that with them and helping them actually look at it. In fact, I just got off a conversation with someone that wants to do process improvement. And I say, he talks about a process improvement job description. And I'm suggesting that what you really like to get to, I don't have it shown here, but is an enterprise process management person, okay, where they're looking at the full value chain to figure out where you should focus your improvement efforts. Because the problem you get into a lot of the improvement efforts that you're working on, the Six Sigma, whatever project, they're not aligned to the metrics that you're actually working on. So what I'm suggesting is you want to create a system so that now the metric improvement needs pull for projects that's going to help the enterprise as a whole. And that's kind of what I'm suggesting that we lead to.
Okay, of course, this person would like to know your opinion on the Johnson transformation distribution.
Yeah, well, the thing is, it doesn't give you the same kind of report out that I'm getting here as far as what you're actually doing. So I don't really use the Johnson transformation.
Okay, here we go. Should you generally make sure ahead of time that you do not have mixtures in your data?
Well, I think the thing is, especially if you're looking at 30,000-foot level view, you're always going to have mixtures in the data of some sort. And so the question is it large enough? George Box, the kind of guru, the designer experiment that unfortunately just passed on just the last month or so ago, is that he made the statement, he says, something to the effect that all models are wrong, some are good, or some are useful, I think he said. And I think that's what I kind of believe also. So, like in this case that I'm showing here, it's not exactly normally distributed, so that might ruffle some people's feathers. But what I'm suggesting, I think it's good enough, even though I really forced it, because that was a simulated data here, to have a very big differences between between subgroup variability. So I think that to me that's kind of good enough. So
okay, we'll just do a couple more and finish. This was from earlier in your presentation. Wanting to know why you were using log standard deviation.
Okay, standard deviation can't get below 0. Okay, now often you just don't have to do that, but if in the normal distribution it goes like to plus or minus infinity. Well, obviously you can't get to minus infinity for standard deviation. So it's like somewhat like the time to do something. You can't get below 0 time. So those tend to be normally distributed. So that makes physical sense in what you're doing.
Okay, we'll do our last one. What should be done to report process capability when there are no specifications?
Yeah. Okay, let's say, for example, this one didn't have a specification to it. Right now it does, so I came up off the x-axis 95 and 105 to figure out the percent. So if I don't have a specification, and that can happen in WIP and also financials, is we don't really have a specification like we're making a widget. For example, the hold time in the call center doesn't really have a specification. We have a desire, but we don't have a specification. But we'd still like to describe how the process is doing. And I like to include variability within the statement like Deming talks about. And so what I do is I pick off of the y-axis the 10, 50, and 90. So then the difference between 90 minus 10 is 80. So I report the median. I'd report the median and 80% frequency of occurrence. I'll just get back to over here. Oops. So anyway, this is has a lot of good questions. I appreciate you attending this webinar here, and this is my contact information. So if you want to touch base with me offline, we have also a lot of we cover this information, our black belt and master black belt training. We also have a 30,000-foot level course that's geared specifically for that. And we have now online coached black belt training, too, that gets into all those details. And it also integrates with the books so that you have more than just a deck of slides after you get done with Six Sigma or Lean Six Sigma training. So, again, thank you for all attending here. And if you got any questions, feel free to call us, and you have a good day.